Hi. So, we are looking at the module on training logistic regression classifier now. So, in the previous module we looked at the basics, a basic idea behind logistic regression, which is essentially to do linear regression with a logistic transformation, right. So, you took the log odds function, which is p of x by 1 minus p of x, took the logarithm of it and tried to fit a linear curve to this transform function, right. So, how do we find these parameters beta 1 and beta naught, right. So, we optimize the likelihood of the training data with respect to the parameters beta, right. So, that is essentially the way we are going to be training this. So, this is slightly different from some of the earlier methods we have looked at identifying parameters, mainly because we are looking at here the probability of classification, not just getting the classifications right or wrong, but we are actually looking at the probability of classification. It makes more sense to try to optimize the probability of seeing the training data with respect to the parameters beta, right. So, what is the likelihood? So, the likelihood is the probability of a training data D given a particular parameter setting beta, okay. So, you should note here that it is a function of the parameter setting, because the training data D that is given to you is usually fixed, right. So, here is an example of the likelihood of some kind of classification task, right. So, I am going to assume that the data is given to you in the form of xi yi pairs, as we have done in the past, right. So, for each xi there is going to be an outcome yi, which will be either 1 if it belongs to class 1 or 0 if it belongs to class 2, right. So, let us look at one term in the product that I have written down there, right. As you can see, if the output corresponding to the xi is 1, right, then the first term in the product will be p of xi, and the second term in the product will be 1, because yi is 1 and 1 minus p of xi is going to be raised to the power of 0, which will essentially reduce to 1. Likewise, if the output corresponding to xi is 0, then the first term in the product is going to be 1 and the second term in the product will remain as 1 minus p of xi, right. So, this essentially means that depending on what the output variable is, I am going to either take the probability of the data point occurring, which I mean the probability of the data point having a label of 1 or the probability of the data point having the label of 0, right. So, do recall that p of xi is the probability that y equal to 1 given xi. So, now for this is for one data point, and if I want to look at the probability of the entire data, I just take the product over all the data points. So, the product runs from 1 to n, right. So, this expression now gives me the probability of seeing the training data given a specific parameter setting. So, where do beta and beta naught appear in the expression on the right hand side? So, p of xi is specified in terms of beta and beta naught. So, implicitly, so beta and beta naught are appearing on the right hand side of the equation, and like I said, likelihood is a function of the parameters and hence we denote it as L of beta. So, now our goal is to optimize this likelihood, and so that so we get a good estimate of the parameter. So, we have to find the right set of betas so that this probability is maximized, right. So, now if you look, this term looks a little hard to optimize because a lot of products here, and so we have to be a little careful. So, the usual way that we operate here is to take logarithms of this likelihood, right, and you can see that lowercase l here is used to denote the log of the likelihood function, and then let us walk through this log likelihood expression a little slowly, right. So, now that I have taken logarithms in the first step, so I have taken logarithms, and therefore, the products that I had earlier have become summations, and the exponentiation that I had earlier have become products. So, that corresponds to the original exponentiation I had in my expression, and now they have become products, okay. Now, we can do a little bit of simplification here, right, and you can see that what I have essentially done is taken in the second step I have expanded the product term in the second term in the summation, right, and then I have gathered terms together which have a coefficient of yi, right. So, and that gives me the second term in the summation, and the first term is just essentially 1 times log of 1 minus p x I, right. So, we know what log of p x by 1 minus p x I is, right, and that is essentially the function that we were trying to fit from the beginning. So, we replace that with our linear fit that we had, the linear regression fit that we did, and then we do further simplification in order to come up with the expression given on the last line. That is essentially writing out p x I and then evaluating 1 minus p x I, and that gives me the negative logarithm term on the last line of the expression. So, now what do? We have the log likelihood. So, what do we do to maximize this log likelihood? We essentially take the derivative of this log likelihood with respect to beta, and then we should be equating this to 0, right. So, the first line here is essentially taking the derivative of the log likelihood, right, and it simplifies to a very nice form, which is y I minus probability of x I, right, times x I, each individual component of x I, and now we set this equal to 0. But we really cannot solve this that easily. Why? Because p x I is actually a transcendental function, right. So, it is not very easy to find a closed form solution for these kinds of expressions. So, we have to actually look at numerical methods for solving these kinds of optimization problems, and we essentially look at a class of algorithms which are known as interior point methods. So, I am not really going to get into the math behind all of this, but I assume that many of you have actually come across a very simple optimization technique called Newton-Raphson method. So, and here is what the expression for Newton-Raphson method is going to look like. So, I start off with a guess for my initial solution, right, the beta, right. I start off with a guess beta naught, and I would typically like my beta naught to be close to the true solution, and once I have the guess for beta naught, then I keep updating the solution by essentially subtracting the first order derivative of the likelihood divided by the second order derivative of the likelihood, take the ratio, right, and then subtract it from beta in order to give me my next estimate, right. So, this has fast convergence under certain regularity conditions. So, for one thing is that the second derivative should exist and should be positive, right, and as you can see, if the first derivative is going to be 0, right, you are not going to be changing the value of your guess, and when would the first derivative be 0? It will be 0 at one of the optimas, whether at the maxima or the minima, and you would also like these. So, since the second derivative is going to be positive till you approach the minima, so you can when you approach the optima, you can be sure that it is going to be the minima, right. So, this is essentially the basic idea behind Newton-Raphson method, and when Newton-Raphson method is applied specifically to the logistic regression problem, you come up with a iterative technique which is called iterative reweighted least squares approach for training for finding the parameters in logistic regression. And so, most of the statistical packages that we have, especially R in particular of interest to us, have a very simple function that allows you to fit logistic regression to any data set that you have, and they will essentially be using Newton-Raphson by way of iterative reweighted least squares technique. To summarize this couple of modules on logistic regression, so logistic regression is a very powerful classifier built on the idea of doing linear regression on a logistic transformed output variable. And the logistic regression is related to exponential family of probability distribution. It arises in a variety of problems, and that is one of the reasons that make them a very popular classifier, right. And apart from that, they work really well. I mean, so that is another reason that logistic regression is a classifier of choice for many people, especially in medical domains, because they allow you to perform what is known as sensitivity analysis. Right. So, you can look at the dependence of class labels on features by looking at the regression coefficient of specific features in the fit that you obtain. Thank you.